Have you ever paused to wonder how everything around us is constantly in motion, and yet we feel so perfectly still our planet spins faster than a jet engine over 1,000 miles per hour while it circles the sun from 93 million miles away? All the while, the entire solar system is darting through the Milky Way at nearly 500,000 miles an hour, and somehow we feel none of it. Our pulse stays steady, our breath stays calm, as if we're sitting inside a perfectly quiet bubble while the universe rushes and spins around us. But what if that calmness, the stillness we take for granted, isn't the truth at all? What if the sense of being still is one of the universe's most delicate illusions? What if time itself is just the faint shadow of a deeper rotation, one that began before atoms or light ever existed? Tonight we're going to drift into that mystery, not to ask why things move, but why nothing in the universe can ever truly stop. So gently close your eyes. Let your body soften. Feel the low cosmic hum beneath your skin and follow me into the quiet, spinning heart of everything. Before we begin, if you feel comfortable doing so, a soft tap on like or subscribe means more to me than you know. It's a small gesture, but I hold it with real gratitude because every bit of your support keeps this tiny corner of the universe glowing and reminds me that these quiet cosmic stories still find their way to gentle hearts like yours. Now, let's step into the first question. Part 1. If everything is spinning, why do we feel frozen in time? Right now, the Earth is rotating beneath your feet at over 1,000 miles per hour. At the same moment, it's orbiting the Sun at nearly 67,000 miles per hour. And as you inhale slowly, the solar system is gliding around the Milky Way at almost 490,000 miles per hour. And yet, your coffee sits perfectly still. The air doesn't rush past your face. The stars look completely motionless. It's one of the gentlest paradoxes of existence, a universe built entirely on motion while we float inside it feeling motionless. From electrons swirling around nuclei, to planets looping around stars, to entire galaxies rotating in vast spirals of dust and starlight, everything spins. Some cosmologists even suggest that the universe itself might carry a faint ancient rotation woven into its structure, an echo from the moment it was born. But why, if everything is drifting and spinning through the cosmos, do we feel so perfectly still? The answer begins with one of the quietest but most powerful truths in physics inertia. Newton captured it centuries ago. An object in motion will keep moving unless something pushes or pulls it. And this simple idea is the hidden reason we never feel the earth turning beneath us. We aren't fighting the earth's motion, we are part of it. Your body, the air you breathe, the oceans, the mountains, every grain of sand, every drop of water, every living thing is carried along in the same smooth rotation. To feel movement, you need change, a sudden jolt, a shift in direction, a force that interrupts the flow. But Earth's spin never changes. It's steady, ancient, the same serene rotation that cradled early humans when they first gazed at the stars. Astronauts experience this calm on an even grander scale. In orbit, They race around Earth at more than 17,000 miles per hour, circling the planet every hour and a half. Yet inside the spacecraft, everything feels weightless, peaceful, untouched by speed. Without air friction, without turbulence, motion becomes indistinguishable from stillness. Physicists call this uniform motion, and it's the same principle that lets you drink tea on a plane cruising at 500 miles per hour. You, the seat beneath you, and the cup in your hand are all gliding in the same direction together. You only feel motion when something disrupts that harmony. Earth's motion has no such disruptions, no shuddering, no drag, no sudden shifts, only a silent, continuous glide through space. And because space itself is nearly a perfect vacuum, there's nothing to whisper to your senses that you're traveling at cosmic speeds. Neil deGrasse. Tyson once said, "We are on a space rock orbiting a star, orbiting a galaxy that's moving through the universe, and we call it home. But our bodies aren't built to feel motion on that scale. Our inner ears were shaped by evolution to notice the tilt of a head, the sprint of a hunt, not the rotation of a planet thousands of miles wide. They detect acceleration, not steady velocity. That's why you feel a car pulling forward, but not the smooth cruise that follows. Here on Earth, everything moves with you. There is no beginning to the motion, no end to it, just a continuous slide through space. And yet, even if we can't sense the rotation, our instruments can. The Foucault pendulum, demonstrated by Léon Foucault in 1851, swings calmly in one direction while the Earth slowly rotates beneath it. Its gentle shift over the hours is our planet's spin made visible. If you've ever stood beside one in a museum, you've watched motion and time intertwine in the smallest, quietest arc. On the scale of worlds, this rotation is anything but trivial. Earth's spin divides day from night, strengthens the magnetic field that shields us from the sun, and keeps temperatures from swinging to deadly extremes. Without rotation, one side of Earth would bake in endless sunlight, while the other froze beneath eternal night. NASA's Goddard Space Flight Center notes that Earth's rotation is slowly easing, slowed by the moon's pull, adding about 1.7 milliseconds to each century's length of day. Even in our stillness, there is change, slow, subtle, but unescapably real. And this spinning isn't unique to Earth. Rotation is a cosmic signature. Stars are born from swirling clouds of gas and dust. As those clouds collapse under gravity, they spin faster and faster, preserving their angular momentum, the same physical law that makes a skater whirl more quickly when she draws her arms in. Every world carries the trace of that ancient momentum. Earth's 24-hour day isn't just a convenience of nature, it's a fossil imprint of the original swirling cloud that gave birth to our planet, even our sun. Massive and seemingly eternal, completes a slow rotation every 27 days, tugging its vast magnetic field through space like luminous strands being woven in motion. And far beyond the Milky Way, our galactic home turns once every 230 million years. A single rotation of the galaxy outlives entire species, entire epochs, entire histories. Each sweep of its spiral arms carries hundreds of billions of stars, all drifting together in a dance that began long before Earth ever existed. The James Webb Space Telescope has looked even deeper so far back that its images are snapshots from over 13 billion years ago. And even in those early galaxies, barely formed, astronomers see hints of rotation. A slight reddening of light on one side, a faint blue shift on the other, the unmistakable fingerprint of spin preserved across cosmic time. It's as if rotation isn't just common, but fundamental, woven into the universe's very blueprint. Yet the question remains, if everything is spinning, why do we feel so utterly still here? Relativity whispers its answer. Einstein taught us that motion has no absolute meaning, only relationships matter. To you and me resting on Earth, we feel stationary, and it is the stars that seem to wheel overhead. From another vantage point, we would be the ones drifting while the universe stands still. This mirroring of perspectives keeps physics balanced and makes our calmness possible. Astronauts aboard the International Space Station experience this paradox firsthand. They orbit Earth at nearly 5 miles per second, yet feel no rush of speed, only weightlessness. Their sense of down changes every 90 minutes, but their minds adapt so completely that motion becomes silence. We are the same. Passengers carried effortlessly through a universe in motion, so accustomed to the journey that the motion disappears. Because if we could truly feel Earth's turn, the sun's pull, the galaxy's drift, if every layer of cosmic movement pressed itself onto our senses, our perception of time would unravel. Motion and time are inseparable. One sculpts the rhythm of the other. Day and night, seasons and years, the slow breathing of the universe rotation sets the tempo. As Carl Sagan once reflected, time is stitched into the very fabric of the cosmos, and we are threads woven into that tapestry. The quiet you feel right now is not the stillness of a world at rest. It is the harmony of everything moving together so smoothly, so perfectly, that the motion becomes invisible. So tonight, as you lie beneath the unseen turning of the stars, remember, you are not motionless. You are drifting through a cosmic river softly, constantly, endlessly. Every moment of silence is simply motion, too gentle for your senses to perceive. Inside that balance of motion and calm life finds its rhythm. Take a slow breath. You are spinning, you always have been, and the silence around you is the sound of everything moving in unison. Now, as we drift a little deeper, it's time to look back past the planets, past the stars, past the galaxies, toward the moment before motion existed at all, before the universe took its first turn. That is where the next chapter begins. Part 2. Who set the universe spinning? If you could rewind the cosmos, not by centuries or millennia, but all the way back to the very first heartbeat of existence, you'd arrive at a moment so small, so strange, that our current physics can barely whisper about it. What would that newborn universe look like? Would there be a flash of light, a thunderous sound, or would you witness something far quieter, a subtle twist, a faint swirl, the first rotation that would eventually echo through stars, planets, galaxies, and you? This question, who set the universe spinning, sounds philosophical, but it sits squarely at the core of physics. It hides inside the earliest sliver of time, within the first 1043 seconds, a period known as the Planck era. At this scale, space-time, matter, and energy are tangled together in ways our equations still can't fully unravel. Yet from the fragments we can decode, one possibility stands out. The universe may have been born with a gentle, primordial rotation. We see its traces today in the cosmic microwave background, the faint afterglow of the Big Bang captured by missions like WMAP and ESA's Planck satellite. Across that ancient light are tiny temperature variations, differences only a few millionths of a degree. Those ripples are the seeds from which all cosmic structure grew: galaxies, stars, planets, oceans, forests, and eventually the living beings listening to these words. But hidden inside that map of faint ripples is something even stranger. Several researchers noticed a faint alignment, a vast, eerie pattern stretching across the sky as if the early universe had a preferred direction. They nicknamed it the Axis of Evil. NASA's WMAP data and Planck's high precision measurements suggest two possibilities. It may simply be a statistical glitch, a curiosity of measurement, or it could be a clue that the entire universe once had a slow global spin. If that second possibility is true, then that ancient rotation may have influenced everything from the shapes of galaxies to the very flow of time. So, how could such a rotation begin? The answer may lie in the quantum fog that existed before anything recognizable formed. Even in perfect vacuum, quantum fields never sit still. They flicker, jitter, and fluctuate. NASA's Goddard Space Flight Center describes them as restless, never truly at zero. When the Big Bang erupted, the universe didn't just expand, it inflated. In a fraction of a second, everything stretched faster than light itself. During that explosive expansion, even tiny quantum jitters were pulled into swirling patterns. Some of those tiny twists became the first cosmic spins. Inflation theory, first proposed by Alan Guth in 1981, explains why the universe looks smooth overall, yet still contains the seeds of structure. But more recent observations, including Planck data and BICEP 2 measurements, hint at something more subtle: B-mode patterns, curling signatures in ancient gravitational waves. These curls are like fossils, remnants of a twisting universe still carrying traces of its first rotation. In this picture, the Big Bang wasn't simply an outward explosion, it was a spiraling birth, a twisting expansion that etched angular momentum into the fabric of reality. And once that seed of motion existed, everything that followed inherited it. As the universe cooled, matter condensed. Quarks became protons and neutrons, which later formed atoms. Every one of them carried a whisper of angular momentum. Later, when gravity pulled atoms together into clouds, then into stars and galaxies, that ancient momentum was conserved, just like a figure skater spinning faster when she draws her arms inward. In physics, nothing begins spinning without cause. Motion must arise from motion. So, if galaxies rotate, if stars spin, if planets twirl, then somewhere woven into the earliest fraction of a second, the universe itself must have carried a tiny primordial twist. And today, astronomers can still see the fingerprints of that ancient rotation in the motions of galaxies billions of light years away. In 2011, astronomers at the Harvard Smithsonian Center for Astrophysics sifted through the rotation patterns of more than 15,000 spiral galaxies. What they found was subtle, almost whisper soft, but unmistakable, a slight imbalance in the direction those galaxies turned. Not enough to declare a cosmic rule, but just enough to make scientists wonder whether this asymmetry is the echo of an ancient spin from the universe's earliest moments. This quiet handedness of the cosmos hints that maybe everything isn't random after all. Maybe there is a hidden rhythm we've never fully heard, a silent turning that everything from planets to galaxies to clusters still follows. Even dark matter, that invisible web holding the galaxy together, might carry its own rotation imprint. Simulations created at NASA's Jet Propulsion Laboratory show dark matter halos drifting, twisting, and slowly rotating across billions of years. These halos cradle galaxies inside them, guiding their motion much like underwater currents guide drifting leaves. Without that gentle rotational support, galaxies would shear themselves apart. It's as if the early universe set everything spinning, and even now that ancient push keeps the stars in balance. Yet the big question lingers: who or what gave the universe its first turn? Physicists often look to a quiet but powerful idea called symmetry breaking. In the earliest fractions of a second after the Big Bang, all the forces we know, gravity, electromagnetism, the nuclear forces, were unified, indistinguishable from each other. But as the universe cooled, those forces began to separate. And when that symmetry split, tiny imperfections emerged. According to the European Space Agency, those tiny cracks in perfect symmetry are what allowed structure, motion, and spin to exist at all. In a universe that was perfectly balanced, nothing could change. But in a universe with a single tiny flaw, everything could move, everything could dance. You can see this principle echoed everywhere in the preferred spin of galaxies, in the orientation of atoms, even in the fact that neutrinos, those ghostly subatomic particles, have a strictly left-handed behavior. Nature is not flawless, and in that gentle imperfection motion is born. Some researchers have tried to measure whether the entire universe carries a collective spin. In 2020, astrophysicist Lior Shamir at Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. His findings suggested a large-scale imbalance: galaxies in one half of the sky favored one rotation direction more than the other. Shamir proposed that the cosmos might possess a faint, ancient pattern of motion, a preferred direction woven into space itself. This wouldn't mean the universe is rotating like a giant cosmic wheel. Instead, it could mean that spacetime carried a slight twist during its early expansion, a twist so delicate that we don't feel it, but so vast that it shaped the motion of galaxies across billions of light years. To test ideas like these, NASA and ESA continue mapping the sky with relentless precision. And now, with the James Webb Space Telescope peering deeper than ever before, we are seeing galaxies whose light began the journey just 300 million years after the Big Bang. And in those distant ancient shapes, astronomers read the faint fingerprints of how rotation first entered the universe. Some of the earliest galaxies Webb has captured already show hints of organized motion spiral structures forming far sooner than theory ever predicted. Too early for randomness, too early for chance, which means the seeds of rotation weren't learned over time. They were present from the very beginning. The universe didn't grow into its spin. It arrived spinning, and when we zoom down from galaxies to the realm of the quantum, the pattern continues. Rotation isn't just a property of planets and stars, it's baked into matter itself. Every electron, proton, and neutron carries intrinsic spin, a built in twist described by quantum mechanics. It isn't spinning the way a planet does. It's a deeper mathematical rotation woven into the particle's identity. Richard Feynman once put it simply: spin is not motion as we know it. A particle has spin the way it has mass. In other words, rotation wasn't added to the universe later, like a decorative detail. It was part of the original architecture. So when you look up at the night sky, you're seeing an inheritance, the cosmic hand-me-down of that first ancient twist. Every swirling galaxy, every orbiting world, every beam of starlight is a descendant of that primeval motion. Without that primordial rotation, matter would never have gathered. Stars would never have ignited. Worlds would never have formed. Time as we experience it would have no pulse. Motion isn't a coincidence. It's the universe's heartbeat. And although we may never pinpoint the exact moment the first spin emerged, the evidence keeps whispering the same story. The universe didn't begin to rotate, it was born rotating. The spin wasn't sparked, it was inherited. Take a slow breath. The atoms inside you, every electron, every nucleus, still carry fragments of that ancient turning. From the smallest particle to the colossal spiral of the Milky Way, the same rotation continues unbroken for nearly 13.8 billion years. We aren't outside that motion. We're part of it, a continuation of a twist older than time itself. And as we drift deeper into this journey, a new question rises naturally from the last: if rotation shaped the universe, could rotation also be the reason life exists at all? That is where we turn next. Part 3. Did spinning make life possible? Without the Earth's rotation, our world would be silent and still. No day, no night, no wind, no oceans in motion. Just one side scorched beneath eternal sunlight, and the other locked in endless darkness, a frozen, airless wasteland. A dead, unmoving sphere drifting through cosmic light. But because the Earth spins, this planet breathes. Every sunrise you have ever seen, every wave that rolls toward the shore, every whisper of wind brushing across your skin, all of it exists because that our planet has been turning since the moment it formed 4.5 billion years ago. Earth's rotation isn't just a movement, it is a life support system, a quiet engine whose steady rhythm sustains everything that breathes. This ancient spin regulates the cycles of temperature, that warm our oceans fuels the winds that carry across continents and helps maintain the magnetic field that shields our world from the sun's radiation. Rotation shapes Earth in ways we can see and in countless ways we never notice. According to NASA's Goddard Space Flight Center, the Earth turns fastest at the equator, about 137 miles per hour, completing one full rotation in 23 hours, 56 minutes, and 4 seconds, a sidereal day. This steady turning is the metronome of our world. Every organism, from the smallest blade of grass to the largest migrating whale, moves, eats, rests, and grows to this silent cosmic rhythm. The most immediate consequence of rotation is the cycle of day and night. As Earth spins, sunlight is spread across its surface instead of locked onto one side. That constant shifting of light creates temperature contrasts that generate wind ocean currents, cloud patterns, the entire machinery of weather. Take away that rotation, and the world becomes unrecognizable. One hemisphere searched under eternal daylight, the other frozen beneath the endless night. Between them, a violent storm ridden boundary where life could never take root. Only because the earth spins do we experience gentle mornings, drifting sunsets, and climates stable enough for ecosystems to flourish. Rotation also feeds the magnetic heart of our planet. Deep below the crust, molten iron swirls and churns. This motion powers a planetary dynamo, a vast magnetic field that wraps around Earth like a protective cocoon. NASA's magnetospheric multi-scale mission describes it simply: the field exists because the core moves. Without this magnetic armor, the solar wind, a continuous stream of charged particles, would strip away our atmosphere just as it did on Mars. Mars still rotates, but its smaller iron core cooled long ago. Its magnetic shield faded, the air thinned, water vanished, and the planet fell silent. On Earth, that same solar wind, meeting our magnetic field, paints the sky with auroras, shimmering veils of green and purple that glow near the poles. They are more than beauty. They are evidence that our planet is still protected, still turning. Earth's spin also sculpts the behavior of the atmosphere. Because the planet rotates, moving air curves a phenomenon known as the Coriolis effect. This gentle bending is what causes hurricanes to spiral, jet streams to flow like invisible rivers, and ocean currents to weave warm and cold water around the globe. Without it, weather wouldn't organize into patterns. It would collapse into chaos. Rotation speed itself determines a world's climate. Simulations from NASA's Global Modeling and Assimilation Office show that planets spinning more slowly can bake on one side and freeze on the other, while planets spinning too quickly may develop extreme winds and unstable atmospheres. Earth's 24-hour rotation sits in a delicate sweet spot, a perfect balance that distributes sunlight evenly enough to create seasons, ecosystems, and life. The length of a planet's day reaches far deeper into life than most people ever realize. Over millions of years, every organism on Earth evolved internal rhythms, circadian clocks tuned to this steady turning. According to research from the National Center for Biotechnology Information, every living cell carries the built-in molecular timekeeper a tiny biological metronome that syncs with Earth's 24-hour cycle. This hidden clock decides when flowers open, when birds begin their migrations, and even when your own body feels tired enough to sleep. If Earth ever stopped spinning, this entire choreography would collapse. Without the regular rise and fall of light, the biological timing that life depends on would dissolve into confusion. Earth's rotation also shaped the story of our moon. Long ago, a Mars sized world, Theia struck the young Earth with unimaginable force. The collision threw molten debris into orbit material that slowly gathered into the moon. That impact also set our planet spinning much faster than it rotates today. Over billions of years, the moon's gravity has pulled against that fast spin, slowing it, gently stretching our days from roughly 6 hours to the familiar 24-hour rhythm we now live by. Tidal forces between Earth and Moon also keep our planet's tilt stable. Without that gravitational partnership, Earth's axial tilt could wobble chaotically, sending climates into violent swings. Data from ESA's Gaia mission confirms that worlds without such stability often face catastrophic seasonal extremes. Earth and Moon now drift through space in a quiet gravitational connection. The same tides that stir our oceans also slow our rotation by about 1.7 milliseconds per century, according to NASA's Jet Propulsion Laboratory. The length of our day, the heartbeat of our world, is changing so slowly that the shift is invisible, yet always happening. In other corners of the solar system, rotation plays roles just as dramatic. Jupiter spinning once every 9 hours and 56 minutes is the fastest rotator of all the planets. Its breakneck rotation drives fierce jet streams and titanic storms. Most famously, the Great Red Spot, a swirling tempest larger than Earth that has been raging for centuries. Its rapid spin does not create calm, but instead distributes heat and sculpts the planet's beautiful banded atmosphere. Venus, on the other hand, rotates backward, and astonishingly slowly, one full rotation takes 243 Earth days. That near motionless spin leaves Venus with almost no magnetic protection. Its dense carbon dioxide atmosphere traps sunlight, relentlessly creating a runaway greenhouse effect that makes it the hottest planet in the solar system. The comparison between these worlds is stark too fast, and storms dominate, too slow, and the shield against cosmic radiation disappears. Even Mars, whose day is just 40 minutes longer than ours, reveals what happens when internal rotation fades. As its core cooled and stopped churning, its magnetic field collapsed, allowing the sun to erode its atmosphere and strip the planet of its oceans. The scattered pockets of magnetism, still etched into the Martian crust, are like fossil echoes of a spin that once protected a dynamic, watery world. Rotation, then, isn't a cosmetic detail of planets, it is a prerequisite for habitability. In 2023, observations from the James Webb Space Telescope examined exoplanets such as WASP 39b and TRAPPIST 1e. The data showed that planets with measurable rotation or atmospheric circulation exhibit more balanced chemical signatures and more stable temperature patterns, clear signs of environments that could, at least in theory, support the foundations of life. Without rotation, a planet's energy becomes trapped or unevenly scattered, creating environments too unstable for life to take hold. NASA's Exoplanet Exploration Program notes that rotation isn't a cosmetic detail. It is one of the key ingredients that decides whether a world can maintain a climate at all. And recent work from the Harvard Smithsonian Center for Astrophysics in 2021 suggests that faster spinning exoplanets tend to keep their molten metallic cores alive for longer periods. A living core means a living magnetic field, and a magnetic field means protection, an invisible shield that preserves an atmosphere and increases the chances that liquid water can survive on the surface. So, when we ask whether spinning played a role in making life possible, the answer echoes from every dataset we have. Yes, rotation influences day length, temperature contrast, atmospheric flow, weather systems, and the very magnetic envelope that keeps harmful radiation at bay. Life doesn't merely tolerate motion, life grows in it. Earth's spin has been slowly changing over geological time, yet its influence continues in every corner of the natural world. The turn of our planet shapes the tides, guides forests in their growth cycles, and times the great migrations of animals. Even our personal sense of time, morning, night, the slow breathing of days, is nothing more than the rhythm created by Earth's rotation. Astrophysicist Neil deGrasse Tyson once put it simply: we are not just in the universe, we are of it. The earth turns, and so do we. If you pause for a moment, you can almost hear that rotation, a low and ancient pulse. Beneath everything, a whisper built up over 4.5 billion years of unbroken motion. If the earth were to stop spinning tomorrow, the oceans would surge toward the poles, the atmosphere would collapse into violent disorder, and our planet would lose the delicate balance that sustains its breath. But tonight, as it turns softly beneath you, every system still moves in perfect quiet harmony. In that sense, Earth's rotation is less a mechanical motion and more an architect, an unseen engineer shaping the conditions for every sunrise, every breeze, every living heartbeat. The same cosmic swirl that once gathered dust into a planet continues to spin that planet into morning, into weather, into life, into you. And now, as we drift further along this journey, let's follow that rotation outward, beyond where it shapes climates and oceans, beyond where it guides the habitability of worlds into a stranger territory, a place where spinning no longer just moves matter, but begins to bend the flow of time itself. That brings us to our next chapter. Part 4: Can rotation bend time itself? When rotation pushes toward its extreme, it stops behaving like simple movement and begins to behave like a force that warps reality. At high enough speeds, turning objects don't merely move through space, they begin to drag time along with them. Einstein's general theory of relativity, published in 1915, revealed that mass and energy shape spacetime, and that motion, especially rotational motion, can twist that spacetime like a soft fabric. The faster an object spins, the more it spirals the geometry around it. This phenomenon is called frame, dragging one of Einstein's most delicate and astonishing predictions. To imagine it, picture space-time as a perfectly still lake. Now place a massive spinning body, Earth a neutron star, a black hole into that lake. The rotation stirs the water, creating tiny whirlpools. Those eddies aren't in the water, they're in time itself. NASA physicist Francis Everett, who led the Gravity Probe B mission, once said, as Earth rotates, it drags space-time around, with it like a sphere twisting the honey in which it sits. Gravity Probe B launched in 2004 carrying four ultra-sensitive gyroscopes into low Earth orbit. They floated in near perfect free fall untouched by air vibration or friction. Their job was to detect the gentle twisting of space-time caused by Earth's rotation. After a year of data collection, NASA confirmed Einstein's prediction. Earth drags space-time by about 0.00011 degrees per year, a number unimaginably small, yet perfectly consistent with relativity. A rotation so soft you cannot feel it. A distortion so subtle only the quietest instruments can detect it. But real, absolutely real, even our calm and modest planet, turning once every 24 hours, has enough rotational energy to bend the passage of time ever so slightly. Now imagine that same effect amplified to an unimaginable extreme, a rotation not once per day, but hundreds of times each second, wrapped inside a gravitational field so intense it crushes atoms themselves. That is the realm of neutron stars. When a massive star reaches the end of its life, its core collapses under its own immense gravity. The pressure becomes so overwhelming that protons and electrons are squeezed together, forming neutrons packed tighter than anything else in the universe. The result is a city sized sphere barely 12 miles across, yet heavier than our entire sun. And because angular momentum must be conserved, the new object spins furiously, as fast as 700 rotations per second. Astronomers call these cosmic engines pulsars because their tilted magnetic poles emit narrow beams of radiation that sweep across space like the arms of a galactic lighthouse. Each pulse is a rotation, a tick of a stellar clock more precise than any made by human hands. And with every turn, these stars produce magnetic fields trillions of times stronger than Earth's twisting spacetime, so violently that even light struggles to follow a straight path. NASA's NICER instrument on the International Space Station has mapped these distortions in exquisite detail. Its measurements show that time near a neutron star flows more slowly than it does here on Earth. The faster the spin, the deeper the gravity, and the slower the ticking of any clock trapped nearby. Einstein predicted this long before we could observe. Time itself dilates in the presence of great mass or rapid motion. Near such a rapidly rotating body, space-time doesn't sit still. It is dragged along with the rotation. You can not remain motionless. There you are compelled into orbit, swept up as if the universe is turning you with it. This is frame dragging at its most dramatic expression. But even neutron stars pale beside something stranger, Kerr black holes that spin. In 1963, mathematician Roy Kerr found the solution to Einstein's equations that described a rotating black hole. Unlike non spinning black holes, which simply pull inward, a Kerr black hole spirals the very fabric of space time around its axis, close enough to the event horizon that rotation approaches the speed of light itself. Nothing, not matter, not light, not even time, can refuse to join the swirl. The region outside the event horizon, where this dragging becomes unavoidable, is called the ergosphere. Inside this boundary, you cannot stay still relative to the wider universe. Every particle, every ray of light, every atom is forced to rotate with the black hole. It is as though space-time transforms into a massive invisible whirlpool, pulling everything into its spin. In 2021, observations from NASA's Chandra X-ray Observatory captured matter spiraling around the supermassive black hole in galaxy M87. The motion matched precisely what relativity predicts for a black hole spinning near its maximum possible speed. Inside that whirlpool, time itself bends. If you could somehow hover just outside the ergosphere, safe from falling inward, but close enough to feel the drag, your minutes would stretch, your seconds would lengthen. For every moment you experience, hours might pass for the rest of the universe. Time would no longer behave as something fixed, but as something elastic, shaped by the fury of the rotation beneath you. Einstein called this the warping of time, the combined effect of gravity and motion working together to sculpt the very rhythm of reality. As Einstein once reflected, time and space are not conditions in which we live, but modes in which we think. And nowhere is that more evident than in the places where rotation becomes strong enough to sculpt reality itself. When the Event Horizon Telescope released the first image of a black hole in 2019, and later the unforgettable portrait of Sagittarius A, the supermassive heart of our own galaxy, what we saw was not the black hole at all, but the light orbiting it. A glowing ring of matter spiraling inward, its photons stretched, delayed, and twisted by the curvature of space-time. Those arcs of light are more than an image. They are a direct confirmation that gravity and rotation can bend not only the paths of stars, but the passage of time itself. And this bending isn't confined to distant galaxies or cosmic monsters. Even the satellites orbiting Earth feel it. The GPS network, those quiet machines that guide our maps, our airplanes, and even our smartphones, must constantly correct for time, dilating in two different ways. Gravity slowing the clocks in deeper gravitational fields, and just speed slowing clocks moving rapidly through space. Without these continual corrections, GPS time would drift by 38 microseconds every day, just enough to push your location several miles off course. So even here, in our peaceful corner of the cosmos, relativity whispers into our daily lives. But when astrophysicists model the regions near a spinning black hole, a Kerr black hole, the calm dissolves into something extraordinary. Their rotation becomes so intense that space-time doesn't bend gently, it twists. In these simulations, the mathematics predicts something astonishing. Closed time-like curves, paths through space-time that loop back onto themselves. trajectories where, in theory, a particle could return to an earlier moment. We don't yet know whether these loops are physically possible, but they emerge naturally from Einstein's equations, as if the universe itself allows for the possibility that time might fold like fabric under the right conditions. The James Webb Space Telescope has added new layers to this mystery. By studying the infrared glow of quasar accretion disks, those spinning superheated halos around the largest black holes, JWST has revealed spectral fingerprints of time dilation. Light from the inner disks is stretched and reddened, slowed by the extreme curvature of spacetime. Some of these photons began their journey more than 13 billion years ago, carrying with them a record of how time flowed near those ancient spinning giants. Rotation, it seems, isn't just a motion. It is an influence, a sculptor of time itself. The faster and denser the spin, the deeper the twist in spacetime. What we call now is not universal. It changes from one environment to another, from a drifting planet like Earth to the raging core of a distant galaxy. Even light, the universe's ultimate speed limit, must bend, hesitate, and sometimes orbit in circles when strong rotation commands it. NASA's New Star and XMM Newton missions have captured soft X ray echoes around black holes, flashes of light, delayed, detoured, and looped by rotation before finally escaping into space. In those echoes, time stretches like taffy, predictable, measurable, but endlessly strange. And so the question arises naturally: if black holes can twist time on local scales, could the universe itself be rotating in some faint, imperceptible way? While data from the Planck satellite suggests no strong evidence for overall cosmic rotation, cosmologists hesitate to declare the case closed. Even the slightest universal twist could leave threads in the polarization of ancient light. Subtle fingerprints hinting that time itself might have a preferred direction, a cosmic arrow, a slow turn woven into the fabric of everything. As physicist Kip Thorne once explained, the same mind who guided much of the science behind Interstellar, when you stand near a spinning black hole, the rules of time no longer feel familiar. In that warped geometry, the future of one observer can become the past of another. Rotation doesn't simply bend paths, it bends the order of events. It settles into the very rhythm of existence and quietly rearranges what before and after even mean. And yet, for all its strangeness, this isn't chaos. It's consistent, it's measurable. Time dilation around rotating bodies has been recorded by atomic clocks on airplanes, satellites, and mountaintops. Move faster or step deeper into gravity, and your seconds stretch. Climb higher or slow down, and time loosens its grip. It isn't a trick of perception, it's the universe keeping perfect score. So, yes, rotation can bend time, but the deeper mystery is why that bending follows such precise rules, such a smooth equation that ties energy, gravity, and motion into one unified flow. From Einstein's field equations to every timing correction applied to a GPS satellite, the evidence whispers the same idea. The universe doesn't merely drift through time, it generates time through motion. Take a slow breath. Right now, the seconds you're living in are written by Earth's gentle, turning the sun's gravity, the Milky Way's slow galactic swirl. Your entire sense of now flows from a choreography of spins so smooth you never feel them. And if rotation can sculpt time, what happens when time begins to influence the spin itself? That's the question waiting in our next chapter. Part 5. If spin shapes time, who shapes the spin? Every moment you experience is tied to something in motion. The tick of a clock, the beat of your heart, even the stability of atoms, all rely on rotation. Electrons carry quantum spin within yet atoms. Earth completes its turn every 24 hours. And while it spins, it tugs ever so slightly at spacetime, slowing the flow of time near the equator and quickening it near the poles. Not because of heat or pressure or altitude, but because relativity demands it. Motion and gravity stretch and compress time depending on how fast you move and how deep you fall into a gravitational well. So, yes, spin controls the flow of time, but we're left with the deeper, more haunting question: who or what controls the spin? To approach that answer, physicists turn to the most precise timepieces humanity has ever built: atomic clocks. Inside each one, electrons jump between two fixed energy states of a cesium 133 atom. Each jump emits a photon with a perfectly predictable frequency. That frequency, 9,192,631,770 cycles per second, defines the length of a second for the entire world. Every moment you live, every digital clock, every GPS satellite, every countdown, every heartbeat, measured in time, all of it is synchronized to a tiny quantum spin inside an atom. And that spin isn't a literal rotation. Quantum spin is deeper, stranger. It's a built in property of matter woven into the universe, the way mass and charge are, not added, not learned, simply there from the beginning. In quantum mechanics, every particle carries a built in spin value, a tiny whisper of angular momentum that decides how it behaves in magnetic fields, how it bonds with other particles, and even how it obeys the Pauli exclusion principle, the quiet rule that forbids two electrons from occupying the same quantum state. At the smallest scale, we know timekeeping itself emerges from these spins, not from the turning of a planet, but from the internal rotations encoded in the architecture of atoms. And just as these quantum spins govern the seconds ticking inside our labs, the far larger spins of planets govern the sweeping rhythms of cosmic time. Earth's rotation dictates the length of a day. Its orbit defines a year. But these motions, though ancient, are not fixed. They drift slowly, gently, almost imperceptibly. The moon's tidal pull tugs on Earth like a cosmic brake, adding roughly 1.7 milliseconds to the length of each day every century. To keep the precise, unwavering beat of atomic time aligned with the drifting rhythm of Earth's rotation, scientists occasionally insert leap seconds into the world's clocks. A tiny adjustment, just 1 second, yet it's our way of reconciling human time with planetary time, syncing the heartbeat of atoms with the slow turning of a world. Even clocks placed at different points on Earth disagree. A clock at sea level near the equator where Earth spins fastest ticks ever so slightly slower than one perched high in the mountains or sitting near the poles. This difference isn't superstition, it's relativity in motion. NASA explains it simply: a clock at the equator experiences both faster speed and deeper gravity, so time there runs a few nanoseconds slower each day. It's tiny, but measurable. Your phone silently corrects for all of this. Every GPS satellite orbits Earth at 12,500 miles above the surface and moves at roughly 8,700 miles per hour. Up there, gravity is weaker and speed is higher, so the atomic clocks aboard each satellite run faster, about 38 microseconds per day. Left uncorrected, your map would drift by miles within hours. So engineers weave Einstein's equations into the software of every GPS signal, constantly adjusting for the warping of spacetime caused by Earth's motion and spin. Each time you open a map, you are, without realizing it, watching relativity keep your feet in the right place. But beneath all these corrections lies the deeper question: who started the spinning in the first place? Astronomers trace it back to one of the oldest laws in physics: angular momentum, the rule that says rotation cannot simply appear or vanish, it must be inherited. 4.5 billion years ago, the solar system began as a cloud of dust and gas collapsing under gravity. As it shrank, it spun faster, exactly like a figure skater pulling in her arms. That original swirl distributed angular momentum into every grain of matter: the sun, the planets, the moons, all of them carried fragments of that motion. No invisible force keeps Earth spinning today. It continues because nothing is resisting it. In the frictionless dark of space, a spin can last for billions of years. So the answer to who controls the spin is, in a sense, no one at all. Once set in motion, the universe doesn't require a hand to keep turning. It simply preserves the movement it already has. But the deeper you look, the stranger the relationship between spin and time becomes. Inside, atoms' spin determines energy states. Across planets, spin defines days. Around massive stars and black holes, spin bends spacetime itself. And all of these scales, quantum, planetary, cosmic, are tied together by a single rule: angular momentum is conserved. Time, viewed from this perspective, isn't a separate backdrop. It's a reflection of how energy and spin interact moment by moment at every level of the universe. In 2016, the Gaia mission mapped the motions of over 1 billion stars in the Milky Way, revealing a galaxy alive, with rotation streams of stars curling through space, tidal tails bending across the sky, and ancient clusters still moving in patterns laid down billions of years ago. A reminder that the universe is not still, and time as we experience it is just the shadow of that endless motion. Motion is self sustaining, it is the quiet balance that underlies both time and existence. And yet, the deeper we follow this thread, the thread of rotation, of rhythm, of the universe keeping time with itself, the more we discover something even more profound: spin doesn't just govern the universe, it remembers it. Angular momentum is one of the most perfectly conserved quantities in all of physics. Once given, it is never truly lost. It transfers, it transforms, it stretches across billions of years, but it doesn't vanish. And so the spin of every star, every planet, every atom is a faint fingerprint of everything that came before. The rotation of Earth today carries the memory of the swirling cloud of dust that birthed it. The spin of the sun carries the memory of the ancient nebula that collapsed to form our system. The spin of our galaxy carries the memory of the cosmic filaments that tugged it into shape. Even the quantum spins inside your body, inside your blood, your neurons, your breath carry the memory of the very first seconds after the Big Bang. You are, in a literal sense, built from ancient rotation. And if the universe sustains its motion in perfect balance, then the next question rises naturally, almost like a whisper. If motion sustains itself, what sustains us? What role do we play inside this grand turning? To answer that, we turn to the last and perhaps most intimate scale of all the human scale, because the same laws that govern galaxies also shape you. Just as stars orbit the galactic center, electrons orbit the nuclei of your atoms. Just as Earth's rotation creates day and night, your circadian rhythms rise and fall with that turning. Just as gravity and spin bend spacetime, your brain bends time inward, compressing memories, stretching anticipation, shaping your experience of the present. Even your heartbeat follows a rhythm, a pulse, a repeating cycle, its own form of spin. Every breath you take is a rise and fall, an oscillation, a rotation of air in and out of your body. So when you ask who controls the spin, the answer becomes both cosmic and deeply personal. You do, and you don't, because you are part of the same motion that created the stars. The universe spins, and so do you. Its rhythms echo through your biology, your mind, your moments. Every night when you lie down to sleep, your consciousness drifts into that same timeless current, into the rotation that has been unfolding for 13.8 billion years. Awareness slows, thoughts circle, time stretches and softens just as it does near massive bodies in space. You enter your own private space-time, shaped by the motions within you, and this is where the idea becomes almost poetic. The universe doesn't just control the spin, it shares it with you. You are not outside of the cosmic rhythm. You are inside it, an expression of it. Every cell, every atom, every thought is participating in a larger turning, which leads us gently, inevitably, to the next question. If the universe spins and we spin with it, why do we experience time so differently from the cosmos that gave us birth? Why does time race in our minds while galaxies drift slowly through the dark? That is where the next chapter begins. Part 6. Why does time feel different for us than for the universe? Their experiment showed something astonishing. The universe does not treat matter and antimatter perfectly the same. A tiny, almost imperceptible preference tips the scales just enough for matter to win by the thinnest margin imaginable. Without that imbalance, you wouldn't be here. Not a single star, not a single atom, not even a whisper of light. The universe exists because symmetry broke. And this theme repeats itself at every scale of reality. When the Higgs field emerged fractions of a second after the Big Bang, it didn't settle perfectly evenly. It froze into a slightly lumpy state, like water forming crystals with tiny imperfections. Those imperfections gave particles mass. Mass allowed gravity to gather matter. Gravity allowed stars to burn. Stars forged carbon, oxygen, nitrogen, the elements within your blood and bones. So when symmetry broke, the universe didn't fall apart. It began. As physicist Frank Wilczek, winner of the 2004 Nobel Prize, once said symmetry breaking is nature choosing a direction, and that choice creates reality. But symmetry didn't just break once, it kept breaking layer by layer, each fracture opening the door to something new. When gravity separated from the other forces, space and time formed their structure. When the strong force separated atomic nuclei became possible. When the weak force decoupled, light flooded the universe. Every time a symmetry broke, the universe became more complex, from a smooth sea of energy into a cosmos filled with galaxies, stars, planets, and eventually life. Even today, you carry the signature of broken symmetry. Your heart beats on the left. Your organs aren't arranged mirror symmetrically. Your brain hemispheres specialize differently. Your DNA twists in one direction, only right-handed helicity. Life is asymmetrical from the molecular level up. As astrophysicist Ethan Siegel once wrote, symmetry is beautiful, but asymmetry is interesting. Asymmetry is what makes the universe alive. And symmetry breaking didn't just shape matter, it shaped time. Before symmetry broke, time may not have had a direction. No past, no future, just a quantum haze of possibilities. But once the forces split and matter clumped, entropy began its climb. Order became disorder. Heat flowed from hot to cold. Stars ignited and burned out. Time gained its arrow. The future became different from the past because symmetry broke in a way that gave the universe a direction to move toward. And so the question shifts. If the universe began because symmetry broke, is symmetry still breaking today? Cosmologists believe the answer is yes. Dark energy, the mysterious force accelerating cosmic expansion, may be the result of a symmetry that broke long ago but hasn't finished settling. The alignment anomalies in the cosmic microwave background, the imbalance of matter and antimatter, the uneven distribution of galaxies across vast scales, each might be a whisper of an ancient fracture still echoing across space-time. Even your life is shaped by these echoes. You age because entropy increases. Entropy increases because the early universe wasn't perfectly symmetrical. Your heartbeat, your memory, your breath, they all unfold in a one-way river of time, made possible by that first broken balance. So when we ask, did the universe begin because symmetry was broken? The deepest answer seems to be the universe didn't emerge in spite of imperfection. It emerged because of it. And that leads us quietly and inevitably to the next question, the most human of all. If imperfection created the universe, is imperfection the reason consciousness exists? Is broken symmetry not just the engine of stars, but the engine of thought? That is where we drift next. Part 7. Did imperfection create consciousness? Everywhere we look, the universe shows preference, not perfect balance, not exact symmetry, but small biases that appear in the behavior of particles, the rotation of galaxies, and even the chemistry of life. And these small biases are not poetic metaphors, they are measurable physical facts. If the early universe had been perfectly symmetrical matter and antimatter would have formed and annihilated each other in equal amounts. Nothing would have survived. There would be no atoms, no stars, no planets, no biology. The universe would have been a uniform, motionless field without structure, but because symmetry failed slightly statistically, almost invisibly, matter gained a tiny advantage. That leftover fraction became everything that exists today. This theme repeats at every scale. The large scale structure of the cosmos, the cosmic web mapped by Planck and later by JWST, is a direct consequence of tiny density fluctuations present in the first moments after the Big Bang. These fluctuations broke the uniformity of the early plasma and gave gravity something to work with. They allowed matter to gather to collapse and eventually to form the galaxies we see today. Even fundamental particles show asymmetry. Neutrinos exhibit a left-handed chirality. CP violation in kaons and B mesons demonstrates that the laws of physics treat matter and antimatter differently. These are not philosophical ideas. These are laboratory results confirmed by experiments at CERN and other particle physics facilities around the world. Biology inherits this asymmetry as well. DNA spirals in one direction. Amino acids in living organisms almost always have one specific orientation. These preferences didn't arise from perfect symmetry, but from the small imbalances that existed from the universe's earliest moments. Life evolved within a universe that had already chosen a direction in multiple subtle ways. Even the arrow of time, the fact that you remember yesterday but not tomorrow, may ultimately trace back to this same symmetry breaking. As physicist Sean Carroll explains, the early universe began in a very low entropy state, and this departure from equilibrium gave time a preferred direction. Without that initial imbalance, time might not have a forward direction at all. So, when we examine matter energy structure and even living systems, the same conclusion appears. The universe functions because symmetry did not hold perfectly. Imperfection is not a flaw, it's the mechanism that allowed complexity to exist. And understanding that brings us to the next question. If the universe began because symmetry broke, and if matter structure and biology all rely on these broken symmetries, then what about the mind? What about awareness? Is consciousness itself another product of cosmic imbalance? Did the same physical principles that shaped galaxies also shape the conditions that made a thinking brain possible? That's where we turn next. Galaxies rotate clockwise or counterclockwise in unequal numbers, showing a statistical bias that shouldn't exist if the universe were perfectly symmetrical. The same pattern appears in biology. Molecules essential for life, amino acids, sugars, proteins, have a built in handedness, a property called chirality. Life on Earth uses almost exclusively left handed amino acids and right handed sugars, a preference so consistent that it defines every living organism. What makes this remarkable is that life emerged billions of years after the Big Bang, yet its chemistry still reflects an asymmetry that began in the earliest fractions of a second. The universe's first imbalance didn't fade away. It propagated through matter, through stars, through planetary chemistry, and eventually into the structure of the molecules that allow you to think, breathe, and exist. This connection between cosmic asymmetry and biological structure has become a major focus of modern astrobiology. A 2020 study by NASA's Astrobiology Institute proposed that polarized ultraviolet light from the first stars could have selectively destroyed right-handed amino acids, leaving left-handed ones to survive in greater abundance. If this scenario is correct, then even the chemical foundation of life traces back to the same broken symmetry that shaped the cosmos itself. Another line of evidence comes from the cosmic microwave background, the faint afterglow of the Big Bang. The Planck satellite detected subtle patterns in its polarization, including small swirling features known as B modes. These features may contain the imprint of primordial gravitational waves generated during cosmic inflation. If confirmed, they would represent direct evidence that the universe experienced a rapid expansion with slight rotational distortions, marking the very moment when perfect symmetry failed and motion became possible. Across all scales, the conclusion aligns. Symmetry is aesthetically appealing, but in nature it is fragile, and each time symmetry breaks, structure appears. As physicist Murray Gell-Mann once noted, if the universe were perfectly symmetrical, no complexity could form. There would be no gradients, no motion, no clumping of matter, no chemistry, nothing to differentiate one region from another. Without those slight imperfections, the universe would be static and empty. When we observe distant galaxies with instruments like JWST, we are effectively looking at the fossil record of that first broken symmetry. The arrangement of clusters, filaments, and voids all reflect the early fluctuations in density and temperature that inflation amplified. Those fluctuations became the blueprint for the cosmic web, the architecture that still governs the large scale structure of the universe. And you sitting here tonight are part of that same chain. The matter in your bones exists because in the early universe, matter outnumbered antimatter by a margin of only one particle in a billion. Every atom in your body is a survivor of that ancient imbalance, preserved since the first millionths of a second after the Big Bang. So when we say the universe began because symmetry broke, it's not a metaphor, it's a physical description. Perfect balance gave way to motion. Motion separated matter from antimatter. That separation allowed stars to ignite planets, to form molecules, to organize, and life to emerge. And as we follow this thread further outward, a new question naturally arises. If broken symmetry creates structure, what keeps that structure from flying apart? Stars orbit the centers of their galaxies faster than visible matter alone can explain. Entire clusters rotate in ways that should tear them apart. If the universe is built on motion and imbalance, then something unseen must be providing the extra gravity that holds everything together. And that leads us into the next mystery one, hidden in the dark spaces between galaxies. Hubble's images of galaxy clusters, such as Able 1689, reveal dramatic arcs of stretched starlight evidence that enormous amounts of invisible mass lie between us and those distant galaxies. The visible matter alone cannot account for such intense lensing. Only dark matter, with its enormous gravitational influence, can bend light to that degree. This phenomenon isn't a theory resting on a single line of evidence. It appears everywhere we look. In 2006 observations of the Bullet Cluster, a collision of two galaxy clusters, provided one of the clearest proofs. As the clusters passed through each other, hot gas slowed down and clumped in the center. But the gravitational mass mapped through lensing did not stay with the gas. It moved with the galaxies themselves separating from the visible matter. This separation showed that most of the mass wasn't in the gas or the stars. It was in something invisible that barely interacts with normal matter at all. Dark matter, whatever it is, behaves like a transparent gravitational skeleton. Stars, gas, and dust are just the visible frosting on top of a much larger invisible structure. Simulations from supercomputers, like the Millennium Simulation run by the Max Planck Institute, reveal that the universe evolves along vast filaments of dark matter. These filaments form the cosmic web, the blueprint upon which galaxies assemble and where galaxy clusters grow. And yet, despite decades of progress, we still don't know what dark matter is made of. It might consist of exotic particles that barely interact with normal matter, WIMPs weakly interacting massive particles. Or it could be actions, ultralight particles, predicted by some versions of quantum field theory. Experiments like Lux Zeppelin in South Dakota and Xenon NT in Italy have been searching for these particles for years, listening for the faintest signal of dark matter colliding with ordinary atoms. So far, the detectors remain quiet. There's another possibility dark matter might be a whole zoo of particles as complex as the visible matter we're familiar with. Or perhaps gravity itself behaves differently on large scales, meaning we need to modify our understanding of it. Alternatives like MOND, modified Newtonian dynamics, suggest that gravity becomes stronger at extremely low accelerations. But most observational evidence still favors dark matter as a real substance, not a tweak in the equations. Even on the scale of our own galaxy, the evidence is unmistakable. The Milky Way's rotation curve remains flat far beyond what visible mass can support. Gaia's precise mapping of stellar movements confirms that dark matter extends as in a massive halo, wrapping around the Milky Way, stretching out to nearly 1 million light years. Without this unseen mass, the solar system would orbit differently. The galaxy's spiral arms would shear apart, star formation would collapse. The orderly structure we see across the universe would not exist. Dark matter doesn't shine, flicker, or glow, but its gravity leaves fingerprints everywhere in the motion of stars, in the arcs of gravitational lensing, in the cosmic web traced by galaxies, and in the very shape of the universe on the largest scales. And this leads to a deeper question. If dark matter holds galaxies together, what holds the universe itself together as it expands. Because in the late 1990s, astronomers made a discovery just as mysterious. The universe isn't only expanding, it's accelerating. Something unseen pushes galaxies apart, counteracting the pull of dark matter. Another invisible component of the cosmos is at work. Something not pulling, but pushing. And that is where the next chapter begins. This means that the cosmos we observe is just a thin layer floating atop a far larger, darker foundation. The universe is not built from what we see, it is held together by what we cannot. And yet, dark matter is only half the mystery. Because while dark matter slows the expansion of the universe through its gravity, another force does the opposite. Something pushes space apart, accelerates it, stretches it. Something even more mysterious. In 1998, two independent teams studying distant Type Ia supernovae standard candles used to measure cosmic distances found that galaxies were not just moving away from us, they were accelerating away. The expansion of the universe was speeding up. This discovery shocked cosmologists. Gravity should slow expansion over time, not increase it. Something must be counteracting gravity on the largest scales. Something invisible, uniform, and incredibly powerful. Scientists named it dark energy. Dark energy doesn't cluster the way matter does. It doesn't form halos or filaments. Instead, it acts like a constant pressure embedded in the fabric of spacetime. As space expands, more of this energy appears driving expansion even faster. The European Space Agency's Planck mission, analyzing the cosmic microwave background, confirmed that dark energy dominates the universe today. Its effect grows stronger as space grows larger. Ordinary matter becomes increasingly diluted, but dark energy remains constant. This creates a future very different from the one dark matter alone would shape. If dark matter is the scaffolding that holds galaxies together, dark energy is the force that pushes those galaxies apart. Together, they define the cosmic dance. But what is dark energy exactly? We don't know. Leading theories propose a cosmological constant, Einstein's lambda, a property of space-time that naturally drives expansion, a dynamic field called quintessence, an evolving energy field that changes over time. A sign that gravity behaves differently on cosmic scales, meaning our equations may be incomplete. NASA's Roman Space Telescope and ESA's Euclid mission are now mapping billions of galaxies to understand how cosmic acceleration has evolved. Their data may reveal whether dark energy is constant or evolving, a clue to its nature. But even without fully understanding it, we can already see its effects. Dark energy will eventually dominate everything. Far in the future, galaxies beyond our local group will slip beyond our cosmic horizon. Their light will never reach us again. The universe will grow emptier from our perspective, a slow stretching into the dark. Carl Sagan once said, "We live in a universe of almost unimaginable vastness." What he didn't live to see was how rapidly that vastness is increasing. Take a slow breath. Right now, you are held gently between two invisible forces: dark matter pulling inward, dark energy pushing outward. You are balanced between them, between the force that binds galaxies and the force that drives the universe apart. And that balance leads us toward the final and most human question in this journey. Because if the universe is shaped by forces we cannot see, if most of what exists is hidden in darkness, then where does that leave us? That is where the next chapter begins. One of the strangest facts in all of biology is that life only uses one of those hands. Amino acids are almost always left-handed. Sugars in DNA are right-handed. We have chose a direction, and every organism on Earth has followed it ever since. Yet the universe itself shows preferences too. Galaxies prefer one spin over another in certain regions. Neutrinos always rotate in a left-handed way. Even the earliest patterns in the cosmic microwave background show subtle asymmetries. That raises a profound possibility. Is life's handedness an echo of the universe's first broken symmetry? Scientists have been wrestling with this question for decades. In 1957, physicists Qian-Xiong Wu and her team performed a landmark experiment showing that the weak nuclear force violates mirror symmetry. In other words, nature treats left and right differently. Neutrinos, all of them, spin left-handed. Their mirror image counterparts simply do not exist in our universe. This discovery shook physics so deeply that it earned Nobel Prizes, and it opened the door to an even larger question. If the universe prefers left at the particle level, could that preference have influenced chemistry in the early solar system? Some evidence suggests exactly that. Meteorites like the Murchison meteorite, which fell in Australia in 1969, contain amino acids with a slight excess of left-handed forms. These molecules formed long before Earth existed, hinting that life's preference might predate life itself. NASA's Astrobiology Institute proposed a compelling hypothesis in 2020: polarized ultraviolet light from newborn stars, light twisted by magnetic fields or scattered by dust, may have destroyed right-handed amino acids more readily than left-handed ones. Over millions of years, this cosmic filtering could have seeded early Earth with a bias toward one molecular hand. If true, the direction of life, the way your DNA curls and your proteins fold, might trace back to processes occurring in stellar nurseries billions of years ago. But there's an even deeper question. Could large-scale cosmic rotation, the same pattern we see in galaxies, have influenced molecular chirality too? Some researchers think so. If the early universe contained even a subtle global rotation, it could have imprinted a directional bias in the distribution of radiation magnetic fields or neutrinos. These fields could then have nudged prebiotic molecules toward one chirality. It doesn't require a strong push, just a tiny preference amplified over billions of reactions could lock biology into one direction forever. As physicist Tisvi Piran once wrote, life may remember conditions of the early universe in ways we have not yet uncovered, and that might be exactly what chirality is: a biological fossil of a cosmic choice. Take a breath. Right now, every protein in your body is folded left-handed. Every strand of your DNA twists to the right. You are built from molecules that follow a rule older than Earth, older than the Sun, older than the galaxy itself. So when we ask whether the universe's spin determines the spin of life, the most honest answer is it's possible, maybe even likely, that life carries an ancient directional imprint from the cosmos. And this brings us to a deeper, almost unsettling thought. If life inherits the universe's asymmetry, then what other parts of existence, motion, time, consciousness, might also be following a pattern we haven't yet recognized? Because if the smallest molecules remember the earliest twist of the cosmos, what else might? In 1956, physicists Qian Sheng, Wu Tsung-Dao Li, and Chen-Ning Yang revealed one of the most surprising discoveries in modern physics. Through Wu's groundbreaking beta decay experiment, they showed that nature does not treat left and right equally. Under certain nuclear interactions, particles consistently prefer a left-handed orientation. This phenomenon, known as parity violation, overturned a long-held belief that the laws of physics were perfectly symmetrical. Their results demonstrated that some fundamental processes inherently choose a side-breaking mirror symmetry at the deepest level. That finding earned Li and Yang the Nobel Prize and laid the foundation for our modern understanding of chirality in both particle physics and chemistry. This imbalance, the universe's tendency to favor one orientation over another, may be the root of the handedness seen in biological molecules billions of years later. The same preference that appears in neutrinos and weak interactions echoes upward into the chemistry of amino acids, sugars, and the spiraling architecture of DNA. What began as a tiny asymmetry in the earliest microseconds of the universe eventually became a defining feature of life itself, subtly shaping the molecular structures that make biology possible. They showed that the weak nuclear force, one of the universe's four fundamental interactions, doesn't treat left and right as equals. Wu's landmark experiment revealed something profound. The laws of physics themselves contain a built in preference. Nature may look symmetrical at first glance, but its foundations are subtly biased. Once you understand this, it becomes far easier to see how life's own molecular directionality could arise from the same underlying asymmetry. Everywhere on Earth, this bias quietly repeats itself. Hurricanes curl in opposite directions, depending on the hemisphere. Seashells trace consistent spirals, and countless biological structures follow predictable twists. Spin and imbalance aren't exceptions, they're part of the blueprint of nature. Even our planet expresses this preference. Earth's rotation creates the Coriolis effect, shaping the direction of massive storm systems counterclockwise in the north and clockwise in the south. Our magnetic field, though it flips occasionally, still maintains a dominant polarity over long eras. Directionality is woven into the world we live in. And when we look out into the cosmos, the pattern becomes even more striking. In 2011, astronomer Leor Shamir analyzed tens of thousands of galaxies captured by the Sloan Digital Sky Survey. He discovered a slight statistically meaningful imbalance in how many galaxies rotated clockwise versus counterclockwise. This wasn't mere chance. It hinted at a large-scale directional preference, potentially a lingering echo of the universe's earliest motion. If such a bias can stretch across billions of light years, it's not unreasonable to imagine that the same ancient asymmetry helped shape the molecular architecture of life. This idea, the bridge between cosmic motion and biology, has fascinated researchers for decades. A 2021 study from the Tokyo Institute of Technology simulated how circularly polarized light interacts with amino acids in the cold darkness of interstellar clouds. The results showed that even a faint excess in photon spin could slowly shift molecular chirality over time. In essence, light shaped by cosmic rotation may have steered prebiotic molecules toward one preferred hand. And remember, light itself carries angular momentum. Photons can be left handed or right handed, and that polarization affects how they interact with matter. When the first starlight passed through magnetized dust, twisted by galactic rotation, its polarization could imprint a subtle bias onto the molecules it touched. Even the simplest grains drifting between stars may have scattered this polarized light in a way that favored certain molecular orientations, seeding asymmetry long before any planet existed. Today, the James Webb Space Telescope is detecting complex organics in star forming regions like the Taurus Molecular Cloud and the Orion Nebula. JWST's infrared instruments reveal prebiotic compounds, carbon chains, nitriles, and other precursors forming under polarized starlight. These findings suggest that the chemical seeds of life may have inherited their directionality straight from the cosmic environment itself. So, when we ask whether the universe's spin set the direction of life, all signs point toward a quiet, persistent yes. From the rotations of galaxies to the handedness of neutrinos, from polarized starlight to the chirality of amino acids, nature repeatedly leans toward one direction. The same cosmic asymmetry that shaped the motion of galaxies may also live within the spiral of your DNA. Galaxies rotate in different directions, but not in equal amounts. That imbalance appears at every scale. Even the molecules that make life possible, amino acids and sugars, carry a built in preference, a handedness known as chirality. Biology depends on that asymmetry. Despite forming billions of years after the Big Bang, living chemistry still reflects the same ancient directional bias woven into the early universe. Researchers have long been fascinated by this link between cosmic structure and biological handedness. A 2020 study from NASA's Astrobiology Institute suggested that polarized ultraviolet light from early massive stars may have selectively destroyed right handed amino acids, leaving the left handed forms to dominate. If that happened on a large scale, life's molecular direction could have been set before Earth even existed. ESA's Rosetta mission strengthened this idea. When the Philae lander sampled the surface of Comet 67P in 2014, it detected organic compounds with slight asymmetries, suggesting that chiral bias originated in space, not on Earth. That means the orientation of life's molecules may have been inherited from interstellar chemistry shaped by cosmic radiation and magnetic fields. Meteorites point to the same conclusion. The Murchison meteorite, which fell in Australia in 1969, contains dozens of amino acids. Analysis revealed a mild excess of left handed versions. As NASA's Johnson Space Center noted, these molecules preserve conditions from before the solar system formed. The imbalance they carry hints that the universe already favored one molecular orientation long before life assembled those building blocks into cells. The split between left handed amino acids and right handed DNA may also be functional rather than accidental. Some biochemists propose that those opposite twists complement one another, allowing proteins to fold correctly and interact efficiently with nucleic acids. Reverse the orientation, and the chemistry becomes unstable or far less efficient. But the deeper cause likely lies in fundamental physics, not biology. Experiments at CERN and Fermilab show that neutrinos have a consistent left handed spin, a phenomenon known as parity violation. In 1956, physicists Qian-Xiong Wu and Sung-Dao Lee demonstrated this effect experimentally in beta decay, proving that the weak nuclear force does not treat left and right equally. As Wu explained, nature carries a built-in preference even when it appears symmetrical. That same directional bias continues on Earth. The Coriolis effect created by Earth's rotation causes large-scale storms to spin counterclockwise in the northern hemisphere and clockwise in the southern. Shells grow in spirals. Vines twist in preferred directions. Polarity defines our planet's magnetic field, anchoring a sense of orientation that flips occasionally but never disappears. On cosmic scales, the pattern persists. In 2011, astronomer Lior Shamir analyzed tens of thousands of galaxies using Sloan Digital Sky Survey data. He found a small but measurable imbalance between clockwise and counterclockwise rotations. The discrepancy suggested a subtle directional pattern over vast distances, possibly a leftover signal from the universe's earliest moments when its first motions were set. Light itself carries spin. Photons can be left or right polarized, and this angular momentum shapes how they interact with matter. Early starlight passing through magnetized cosmic dust could have imprinted its polarization onto the molecules forming in those clouds. Even simple dust grains drifting through the galaxy may have been aligned by that rotation, scattering light in a way that favored one molecular orientation. The James Webb Space Telescope deepens this picture. By observing star-forming regions like the Orion Nebula and the Taurus Molecular Cloud, JWST has detected prebiotic compounds forming under the influence of polarized radiation. These observations show that the earliest ingredients of life naturally acquire directionality from their cosmic environment. Taken together, the evidence points toward a consistent conclusion. The universe's rotation and its early asymmetries likely influenced the chirality of life. From galactic spin to neutrino handedness, from polarized radiation to molecular orientation, nature repeatedly favors one direction over another. That bias stretches from the largest cosmic structures down to the microscopic spirals inside your cells. When galaxies collide, their stars drift past one another unharmed, but their dark matter halos do interact, trading angular momentum and pushing it outward. Over enormous spans of time, this exchange leaves galaxies rounder and slower their elegant spirals gradually relaxing into more featureless elliptical shapes. ESA's Gaia mission, which has charted the motions of more than 1.8 billion stars, shows that even the Milky Way is slowly settling. Arms that were once firmly coiled are stretching outward. With every passing epoch, gravitational friction, both from surrounding galaxies and from the dark matter filling our halo, bleeds away some of our galaxy's spin. Far into the future, the Milky Way and the Andromeda Galaxy will approach one another not in explosive collision, but in a long, quiet blending. Their individual rotations will merge and diffuse until the two systems form a single, enormous, slowly rotating elliptical galaxy. Yet rotation never truly disappears. It changes shape. When massive stars exhaust their fuel, they collapse in on themselves. As their radius shrinks, their original angular momentum forces them to spin faster, much faster. That collapse gives birth to neutron stars, dense remnants only a few kilometers across that can rotate hundreds of times each second. NASA's NICER instrument aboard the International Space Station has measured pulsars spinning at 716 rotations per second, their beams slicing through space with near perfect regularity. But even these cosmic metronomes gradually slow. As they emit magnetic radiation and gravitational waves, they leak energy into the surrounding void, losing angular momentum bit by bit. As the cosmos stretches into deeper eras, rotation becomes increasingly rare. Stars burn out, stellar remnants cool, and the universe's final engines of spin black holes begin to change as well. In 1974, Stephen Hawking predicted that black holes radiate energy over time. Even spinning Kerr black holes lose mass and angular momentum through this slow evaporation. As they do, they transfer the last traces of their rotation into space-time itself, sending out a faint gravitational ripples that travel across the universe. The future LISA mission, scheduled for the 2030s, will listen for these whispers gravitational waves from merging spinning black holes as they shed their momentum. Each detection will be a fossil imprint of rotation turning into geometry, a record of motion fading into the fabric of space-time. Long after the black holes evaporate entirely, their rotational influence will linger in the curvature they left behind. So does the universe ever truly stop turning, not in the literal sense. Angular momentum cannot be destroyed. It can only disperse, thinned out, diluted among an ever growing ocean of particles and expanding space. As NASA notes, in an isolated system, angular momentum is always conserved, and on the largest scale, the universe behaves much like one. But as eons pass, the remaining spin may become so spread out that it no longer shapes structure in any meaningful way. Motion will still exist, but faintly so subtle and widespread that the universe approaches a kind of quiet equilibrium. In the farthest future, long after the final stars have flickered out and the last galaxies have dissolved into faint smudges of light, the universe will drift into a state physicists call heat death. Energy will be spread perfectly evenly. No gradients will remain. No flow, no cycles, no winds of motion. Spin will still exist as a mathematical property, but with nothing left to contrast against it will lose all physical significance. Some cosmologists, among them Lawrence Krauss and Brian Greene, describe this era as a kind of cosmic hush, the final quiet after every orbit vibration and rotation has been stretched fistum across unimaginable time. In that distant epoch, protons may eventually decay. Black holes, having spent trillions upon trillions of years evaporating through Hawking radiation, will vanish in brief flashes of light. All that remains will be a thin sea of low energy photons and neutrinos drifting endlessly, each carrying a faint imprint of the universe's once dynamic rotation. The James Webb Space Telescope looks deep into the universe's youth, but its images also hint at its fate. Every ancient galaxy JWST captures is another chapter from a time when rotation sculpted structure. The spirals, the filaments, the bright knots of star formation, all of them are signatures of motion in its prime. In those images, beginnings and endings coexist. Rotation ignited by early asymmetry, and rotation that will one day fade into uniform stillness. Yet, even when movement is gone, its traces never fully disappear. The polarization of the cosmic microwave background, the gravitational curvature around remnants of dying stars, these are permanent records etched into space-time. The universe doesn't lose motion, it loses contrast. Motion becomes too diffuse to notice. Take a slow breath. At this moment, Earth's molten core still churns. Stars still loop around the galactic center. The Milky Way continues its long glide through the cosmic dark. Every motion you observe, every orbit, every rotation is a distant echo of that first ancient turning. It will persist far longer than any star, but not forever. And when the deep future finally arrives, when the last spin stretches out into equilibrium, something will remain. Not motion itself, but the imprint of motion. The structure of space-time will still remember that the universe once turned. As this horizon of stillness approaches, a quieter question emerges, not about galaxies or stars, but about us. If everything in the universe is slowing down, what does it mean for beings who are still moving inside it? And so our next chapter begins shifting from cosmic motion to the motion carried in inside consciousness. Part 10. Are we the universe remembering its own motion? Every atom within your body is still in motion. Electrons swirl in quantum orbits. Protons and neutrons vibrate within their nuclei. Even the quarks inside them carry intrinsic spin. None of this movement is arbitrary. It is inherited. It is the faint residue of the universe's earliest rotation. When you lift a hand, when your lungs rise, when your heart contracts, you're not acting apart from the cosmos. You're participating in its oldest pattern. The motion inside you is a continuation of the motion that shaped everything. Angular momentum. The rule that preserves spin is what allows motion to persist across billions of years. It is why galaxies still rotate, why planets still orbit, why atoms continue to hum with quantum energy. NASA's Goddard Space Flight Center explains that angular momentum cannot be destroyed, only redistributed. That means every rotation, from the sweep of a galaxy to the spin of a quark, is linked back to the same primordial motion at the birth of the universe. From the earliest moment, the cosmos was never perfectly still. Measurements of the cosmic microwave background, mapped with extraordinary precision by ESA's Planck satellite, reveal tiny directional differences in temperature, subtle anisotropies that show the universe carried structure and motion even in its infancy. Some cosmologists interpret these subtle temperature variations as remnants of the universe's very first angular momentum, the ancient twist that set all later motion in play. That initial rotation never disappeared. Instead, it broke apart and distributed itself across every scale of existence, from the spin of galaxies to the quantum motion inside atoms. When stars emerge, vast clouds of hydrogen and helium collapse under gravity. As those clouds contract, they speed up, conserving angular momentum in the same way a skater accelerates by drawing her arms inward. From this simple rule come accretion disks around young stars, the birth of planetary systems, and the whirlpool like structures that form around black holes. Every planet and moon carries a portion of that inherited motion. Their orbits are not arbitrary, they are remnants of the universe's first rotation, preserved over billions of years. And inside those worlds, within minerals, oceans, and living organisms, the same pattern repeats on microscopic scales. Even the atoms in your body still hold fragments of that ancient motion. Electrons, which define how atoms bond and how chemistry unfolds, obey quantum spin, a fundamental type of angular momentum built into the nature of particles themselves. This spin is not a physical twirl, but a quantized state that determines how particles respond to magnetic fields. Without it, atoms could not organize, molecules could not form, and matter, as we know it, would collapse into disorder. NASA's quantum science programs describe spin as a stabilizing engine at the heart of atomic structure, the fine distinction that makes the difference between chaos and formation. Seen this way, every piece of matter carries a silent choreography. Spin contributes to magnetic fields. Magnetic fields guide structure. Structure gives rise to stars, planets, and eventually to life itself. Your own neurons operate through electrical gradients shaped by these same electromagnetic principles. Every thought you experience, every pattern of activity in your brain is a carefully arranged motion of charged particles. So, when scientists consider whether consciousness might represent the universe, retaining a trace of its primordial rotation, the idea is not metaphorical. It is grounded in physics. Each brainwave is built on motions that have existed since the universe was young. The faint magnetic fields created by neural firing follow the same laws that govern pulsars, magnetars, and the spinning remnants of collapsed stars. Neil deGrasse Tyson once expressed this connection. Simply, we are not just within the universe, we are built from it, and its processes continue inside us. From a scientific perspective, memory itself is a form of pattern retention, information stored in stable physical configurations. Particles retain orientation through spin states. Cells maintain structure through biochemical arrangements. Stars preserve their histories through rotation curves. and the universe as a whole stores information in the contour of spacetime. Einstein's general relativity shows that energy and momentum shape the curvature of spacetime. Every rotation, no matter how small, leaves a gentle twist, a deformation in the geometry of reality. This effect is known as frame dragging, verified directly by NASA's Gravity Probe B mission in 2011. The satellite measured how Earth's spin subtly drags the space-time around it, distorting its geometry, just as a spoon stirring honey pulls the liquid into a swirl. The experiment confirmed that spin is not limited to objects moving through space. It extends into the space they move through. In the same way, even your own movements, though unimaginably tiny in comparison, create the slightest ripples in space-time. It is a difference of magnitude, not kind. Meanwhile, the atoms in your body spin billions of times per second, their magnetic signatures detectable with the most sensitive quantum instruments. Each tiny rotation inside your body adds to a much older record of movement, one that began long before humans appeared. If every form of motion leaves a subtle imprint on space-time, then what we call awareness may simply be the universe observing those imprints through us, not as mysticism, but as continuity matter recognizing the patterns it has carried since the beginning. In scientific terms, consciousness can be viewed as a system capable of reflecting its own internal state, and that reflection is rooted in movement flows of ions, shifts of electrical charge, oscillations of neural networks, even light. The universe's oldest messenger carries angular momentum. Photons possess spin 1, which determines their polarization and the way they interact with matter. The polarization mapped across the cosmic microwave background is the earliest surviving record of rotational history. ESA's Planck mission and NASA's WMAP spacecraft revealed faint B mode patterns, tiny curling signatures that point to gravitational waves generated during the universe's first moments of motion. When you look at starlight, you are seeing those ancient twists stretched and thinned by billions of years of cosmic expansion. And that same light shaped by primordial rotation enters your eyes, triggers chemical reactions, and becomes part of the electrical motion inside your brain. In that sense, the universe doesn't merely retain its spin, it continues to experience it through every conscious observer it gives rise to. Even as cosmic structures grow colder and spread farther apart, the traces of rotation remain. Galaxies may lose speed, but their angular momentum doesn't disappear. It transfers outward into gas, dark matter, halos, radiation, and intergalactic filaments. The James Webb Space Telescope has revealed faint tendrils of gas stretching between ancient galaxies, structures sculpted by gradual exchanges of angular momentum. Every thread of matter still follows the rhythm established 13.8 billion years ago, and in the far future, when stars grow dim and the universe falls quiet, those patterns will still echo in gravitational waves, in particle spin, and in the faint glow of background radiation. They persist as fossils of rotation motion, preserved as geometry itself. Carl Sagan once said that we are a way for the cosmos to know itself. In the language of physics, that knowing arises through motion energy, and the persistence of spin. The universe writes and rewrites its own history through every process that carries momentum. Take a slow breath. Inside your body, atoms continue to rotate with the same underlying properties that once shaped the first stars. You are a moving archive, a living extension of the universe's long memory. And if memory is expressed through motion, then life may be the brief moment when the universe slows just enough to recognize that it is still turning. Thank you for drifting through this quiet journey with me tonight. If these moments brought you a bit of calm, I'm grateful you chose to spend them here. A gentle like or a soft tap on subscribe truly helps me keep creating these soothing cosmic stories for minds wandering at the edge of sleep. If you're comfortable, share in the comments where you're listening from and what time it is where you are. I love seeing how these small, quiet adventures travel from one corner of the night to another. Wherever you rest, may the universe continue to turn softly around you.